Hi, and welcome to our lesson 3. You can see today we're going to be starting on a new theme, polar coordinates for today. So we're going to introduce you to polar numbers in the polar coordinate plane. The polar plane is one that's specifically designed to work with angles, as you can see. That center point is called the pole. And you could say everything revolves around it. The rings represent the radius of some angle that's going out. So rings represent radius. And the spokes, as you can tell, the spokes represent angles. Or the spokes show angles. So a point in the polar plane has coordinates r for radius or ring number and theta, which represents an angle measure. So r is the radius, and it's helpful if you equate that to ring. Theta is an angle measured in standard position. And you'll remember that standard position means you have your initial side on the, well, it would be the x-axis, or going due east, if you will. So with that little background, we're going to ask you to come down here and we're going to do a series of activities that help us to recognize where points lie in the polar plane. Here's the initial side of the angle for this point, and here's its terminal side. If we're going to name that point, then we need to know which ring number it's on. So it's on the 1, 2, 3, 4th ring. And the angle that's represented there, well, if you think about this in terms of radians, which I hope you will, this is pi sixths. This is pi thirds. You could think 1 pi 6, 2 pi 6, and 2 pi 6 is pi thirds. This is pi halves, or 3 pi 6, and this is 4 pi 6, or 2 pi thirds. Those things are obvious, they're on your unit circle as well. So here we're at 5 pi 6. Here we're at pi, and we could keep going around the ring. You should also remember that angles can be named by a negative angle measure if you do a clockwise rotation as opposed to a counterclockwise. So if we're going to name the point that we've got here, we've got the ring number at 4. The angle is 2 pi thirds. Okay, angle in standard position. One thing that you might be interested in knowing, since our trigonometric functions are periodic, one point can have many names, so that might be a surprise to you, but it could have many names. And I'm going to ask you to list a couple of them here, and we'll explain as we go where those names come from. We obviously could add 2 pi radians to this and end up at, let's see, 2 pi, and we got to be in thirds. So adding 6 pi, 8 pi thirds, we could call it 4 8 pi thirds, which would mean we went in an additional full circle. We could call it, folks, this would be negative pi thirds right here. We could name it as negative pi thirds as the angle. And that's also 5 pi thirds if you're in positive angle measure. However, since this is the angle we're looking at, we had to cross the pole to get to the point, then its radius or ring number becomes negative because you had to cross through the pole. So it's negative 4 because you crossed through the pole. Lots and lots of names could be given to that angle. So now we're going to ask you to do one. We want you to plot the point 2 and pi thirds. So we're looking at our unit circle. Here's the pi thirds spoke. We want to be on the second ring. So there we are right there. So now I want you to plot the point 2 and negative pi thirds. So negative pi thirds is this spoke, and if we want to be 2 on its positive side, then we have to be right here. Okay, we haven't crossed through the pole. That's what makes us positive. Here we want to plot pi thirds, so back on this spoke, but negative 2, you got to cross through the pole to get to the negative territory for that angle. And there it is right there. And finally, negative 2 and negative pi thirds. Here's the negative pi thirds spoke. To plot negative 2 along there, you have to pass through the pole. So there's our guy right there. All right, kind of interesting, and I think we'll be served well if we remember that radiuses become negative when you cross through the pole. Okay, I'm going to ask you to take a look at the polar point 4 and 60, which is plotted up here. It's on the 60-degree angle mark, or pi thirds if you were in radians. So I'll just write that up there. It's on the 4th ring out. If we could, by some magic, layer the rectangular coordinate plane over the polar plane, and fortunately I do have that magic, look what happens there, folks. That point is still a point in a coordinate plane, and it could have its own name in the XY coordinate plane. That is, if we think about this, it had a radius of 4. We could find a y by using the sine of angle 60. We could use an x by using the cosine of angle 60. And remember what we've always said, x goes with cosine, y goes with sine. So the cosine of 60 is equal to x over 4. We need the x if we're going to write this in rectangular coordinate. So our x for this particular point would equal 4 times the cosine of 60. And the cosine of 60, I happen to know, is 1/2. So that is 4 times 1/2, or 2 is the rectangular coordinate. You can see that right there, right? It is on the 2 line. To find the y coordinate, we use the sine, and we think sine 60 equals y over 4. So y is equal to 4 times the sine of 60. The sine of 60 is root 3 over 2. So our y is 4 times root 3 over 2. Or that you can reduce there, 2 root 3. If that y coordinate doesn't look right to you, I just want to remind you, if you look at this point, it doesn't get all the way to 4, so you couldn't say, because if it got all the way to 4, then this diagonal would be longer than 4. That y coordinate is 2 times the square root of 3, and so that point in the rectangular coordinate plane is at 2 and 2 root 3. Let's generalize that for any point in the polar plane. So to find the x, what we did was multiply r times the cosine of theta. And to find y, we multiplied r by the sine of theta. Again, we'll just remind you, you'll get sick of hearing it, but y goes with sine and x goes with cosine. Okay, our job is to find the rectangular coordinates for the polar point 3 and pi. So I would say to you, or stipulate to you, that at pi radians, we're out here on the negative side of the x-axis, and according to this point, we're at some distance that is 3 that way. If this is the origin in the polar plane, then to be on pi radians, we have to be on this spoke, and we have to be on the positive side of the pole for this one. So 3 pi would be that point in the polar plane. This angle is pi radians. Okay, so we have this distance as 3, and we need to get coordinates for this point in rectangular fashion. I think that you can see where this is going, folks. The cosine of pi radians would be its x value 3 divided, or x, actually in the coordinate plane, it's x value -3 divided by the radius, which is 3. We're on the third ring. So the cosine of pi is -1. The sine of pi is 0, because at this spot in a coordinate plane we're not up at all. So to find the rectangular coordinates, now this one you could do just by drawing your picture, but not all of them work that way. To find the so we're going to follow the right procedure. To find the x coordinate, you multiply r, which is 3, times the cosine of theta, and our theta was pi. That is 3 times -1, which is the cosine of pi, or -3. The y for this polar point takes the radius 3 and multiplies by the sine of theta, which is the sine of pi in this case. The sine of theta, or the sine of pi, I beg your pardon, is 0, so the y coordinate is 0. And we are looking at the point -3, 0. These two reference the same point. Okay, they're talking about the same thing. -3, 0 in the rectangular plane, 3 pi in the polar plane. We can find the polar coordinates for a point if we know its rectangular coordinates, and we're going to demonstrate here. We're going to derive some formulas too and show you in general how you do this, but we're going to do it for this point to begin with. The coordinates of that point are 4 and 2, and if you sketch in the right triangle that is made by that point and the positive x-axis, this part is 4, this part is 2, and this would be the radius, which is what we need for a polar point. So the Pythagorean theorem can get us that. In general, r squared is equal to x squared plus y squared. For our example problem here, r squared is 2 squared plus 4 squared, and that would make it, oh, I guess I got those backwards, but you know it doesn't matter. 4 and 16 is 20, so r squared is 20. And r is the square root of 20. 20 is 4 times 5, square root of 4, 2. So r is 2 root 5. And we have the radius part of our polar point. So I'm going to come over here and say we know this part is 2 times the square root of 5. Now we need to get the angle. That's our angle theta right there. Well, we know it's opposite and it's adjacent, so we can use the inverse tangent. In general, that's going to be our scheme. The theta is equal to the tangent inverse of y over x. For our particular problem, that is the tangent inverse of 2 over 4, or 1/2. So let's find out what angle that is. I am in radian mode, and I'm going to keep myself in radian mode. Second and tangent of 1/2, it reduces to. And I have about 0.46 radians. If I needed to, I could turn that into degrees very easily by multiplying by 180 and dividing by pi. I'm going to do that right now. So to turn it into degrees, I multiply by 180 divided by pi, and that is about 26.6 degrees. Okay, we were 0.46 in radian measure, or we were 2 radical 5 and 26.6 in degree measure. Okay, both of those names fit. This note applies to not this example problem, but others that you might find. It says that you should use the signs, SIGNs, of the coordinates of the point to determine what has to be added to the angle measure you get to make sure you're in the proper. You know, I'd like to talk about that real quickly. Tangent inverse gives us values that are either in Q4 or Q1. Remember, those are the principal values for the tangent. So if I look at the coordinates of my point like this and see that I have a -2, 3 point, that puts it over here in the second quadrant. When I do tangent inverse, it's going to tell me some angle measure down here in the negative. I'm going to have to add pi radians to it to get it up here in the second quadrant where it belongs. If we happen to have both coordinates negative, that would put our point in the third quadrant. tan inverse gives us an angle in the first quadrant. We'd have to add pi radians to get that. So you need to be aware of which quadrant your point is lying in, because your angle measure depends on that. So let's try this one. We have an x of -2 and a y of 3, and that puts us up here. There's our point. Okay? We know to find the radius, you use the Pythagorean theorem with x and y. So r squared is equal to -2 squared plus 3 squared, and that means our r squared is 4 plus 9, 13. R then is the square root of 13, and we have one part of the polar coordinates for this point. We have the radius part. It's root 13. To come up with the angle, we do the tangent inverse. So our angle is the tangent inverse of, and it's y over x, so 3 over -2. Let's go to our calculator, second and tangent, and we want -3 over 2. And what that tells us is that we are at -0.98 radians. Okay, -0.98 is down in here somewhere. We need to be over here. So we have to add pi radians to this to get ourselves into the proper quadrant, where our angle is not in 4, it's in 2. So we're going to add pi radians to that, plus pi, and our angle, our theta, is 2.16 about radians. So there are our polar coordinates. Very good, folks. Okay, the conversion equations that we've used so far today can also be used to convert polar equations to rectangular and back and forth. And when we say conversion equations, these are the things that we're talking about. That r squared is equal to x squared plus y squared. That x is equal to r cosine theta. And that y is equal to r sine theta. So those are our tools for converting equations, and we're going to start with this one. It says that we should write r equals -3 in rectangular form. Well, folks, I'd ask you to think about that for just a minute. If r is equal to -3, that means that you're on the third ring out in the polar plane, right? And since it's negative, it just means that you're going to be talking, if your angle is over here, you're talking about this point, but that really doesn't change the fact that you're on the third ring. So our equation is going to be that of a circle. And let's see if we can't come up with that equation. What we know is that r squared is x squared plus y squared. So let's do this. Let's square both sides of this. We would have r squared equals -3 squared, and r squared is x squared plus y squared. So I'm going to substitute x squared plus y squared equals 9. Folks, that is the equation of the circle that has radius 3. I don't know if you remember that from your geometry class. I know that's a long time ago, but x squared plus y squared, that's a circle's equation, and the constant is the square of the radius. So that's the equation of a circle whose radius is 3. We want to get this into polar form. So we're going to think x we know is r cosine theta, but we need x squared. So r cosine theta squared plus, and then it's y, so r sine theta, but minus 1 squared equals 1. Okay, now that does not look encouraging to me, but I do know how to square this. The exponent goes to both places. R squared cosine squared theta plus, and now I can square this one. I'm going to use the box method or FOIL, whichever method you choose. I'll show the box real quickly, but we're doing r sine theta minus 1 in both directions. We're squaring it. So we're going to get an r squared sine squared we're going to have negative r sine twice minus 2r sine theta, and then negative 1 times negative 1 is 1, plus 1 equals 1. Well, we can see that those 1's on either side are going to knock each other out, so we're going to subtract 1 from both sides, and that'll put us at 0. And then you're looking at these three terms over here, so this is equals 0. Three terms. I see right here a sine squared and a cosine squared, so I think I'm going to join those. I'm going to factor an r squared out of both of those. R squared, if I divide this by r squared, I get cosine squared theta. There's a plus sign. If I divide this term by r squared, I get sine squared theta. And then I still have this minus 2r sine theta. Okay, I know that cosine squared plus sine squared is 1. So really, this boils down to r squared minus 2r sine theta equals 0. Okay, this might not be looking that good to you, but folks, we're getting somewhere. There is a factor of r in both of those that could be factored out. So if I divide by r, I get r minus 2 sine theta equals 0. Alright, let's solve this, folks, because solving means setting each of the terms equal to 0. So one of the solutions would be r equals 0. And folks, that's trivial, right? That's a circle that has no radius. So that's a, you could call it an extraneous solution if you want, but that's a trivial solution because that would be a circle with a 0 radius. The other parenthesis, however, gives us something. R minus 2 sine theta equals 0. If that's true, then we can just get r by itself. R equals, and it will be 2 sine. And there you have it. That is a polar equation. It's solved for r, just like this one was solved for r. That's the equation in polar form. So you've done it, and those are the things that we had to talk about today. We'll talk more about polar numbers in school tomorrow, so please get out there and let's do that. You try.